So far, we discussed single issue processes. Its maximum instruction per cycle is 1. To achieve better performance, for example, the instruction per cycle greater than 1, we need to complete multiple instructions per clock cycle. The solution is multiple issue processes. And there are two types of multiple issue processes. One is superscalar processes, and the other is VLIW processes. VLIW stands for very long instruction word. Their approaches are different. Let's begin with the superscalar processes. So again, this is a multiple issue processor, so they issue and complete a varying number of instructions per clock cycle. So they have a multiple instruction pipelines, and they execute either in order or out of order. And the hardware takes care of all data dependency analysis. Because of that, the hardware gets complicated, but most desktop laptop processors are superscalar processors, and this is what you have in your laptop, desktop, and smartphone. The other type of the multiple issue processor is VLIW processors. So the superscalar processors, the hardware takes care of all data dependency analysis to issue multiple the instructions to execute. But on VLIW processors, compiler does most of the analysis. So this is a software approach, while the superscalar is a hardware approach. So again, the idea is the same. So the VLIW processors issue a fixed number of instructions formatted as a one large instruction bundled by the compiler. And compiler checks the dependencies at compile time and groups the instructions into bundles. So compiler gets complicated, but the hardware gets simple. Examples include the Intel Itanium processor and some GPUs and digital signal processors. So depending on the number of instructions bundled into the instruction bundle, we say n-way VLIW processors. For example, 5-way VLIW processors can bundle up to 5 instructions into a long instruction bundle. This is a quick summary of multiple issue processors. So as we discussed, we have superscalar processors and the VLIW processors. So superscalar processors, as hardware approach. So hardware complex, software simple. Exact opposite for VLIW. So compiler gets complicated, but the hardware gets simple. But the idea is the same. They issue a varying number of instructions per clock cycle. So the first 3 rows are different types of superscalar processors, and we have a VLIW and EPIC. So EPIC is Intel's version of VLIW processor, very similar to VLIW. And depending on their scheduling and the execution model, we have a static superscalar, dynamic superscalar, and speculative superscalar. So speculative superscalar are most popular among different variants, and they use out-of-order execution with the speculation. So most the desktop laptop processors are speculative superscalar processors. Now let's talk about the parallelism. So parallelism is a driving force of modern computer design. And there are 3 types of parallelism that we are trying to exploit. So first one is ILP, the instruction level parallelism. We talked about this before. So we use the instruction pipelining and multiple issue techniques to improve ILP. Now the next type of parallelism is TLP, the task level parallelism or thread level parallelism, and we have the example of multi-core processors. And the last type of parallelism is DLP, the data level parallelism, and we have uh, several popular processors for DLP. One is vector processors and GPUs and the SIMD extension engines. Based on the number of the instruction streams and data streams available in the architecture, we have a popular taxonomy called the Flynn's taxonomy. So the first type is SISD, the single instruction, single data. The unit processor is basically SISD machine. And second type is single instruction, multiple data. And we have vector processors, multimedia extensions, SIMD extensions, and GPUs. The third type is MISD, the multiple instruction single data, and we don't have any commercial processor that targets the MISD. The last type, MIMD, so multiple instruction, multiple data streams, we have a multi-core processors. So multi-core processors use a MIMD model. So again, this is called the Flynn's taxonomy, and its taxonomy is based on the number of concurrent instruction streams and data streams. Now let's talk about the task level parallelism, also known as a thread level parallelism. So this is the second type of parallelism out of three, and motivation is so we hit the power wall and heat wall around 2005, so we couldn't increase clock frequency to exploit the ILP further. So the industry changed the direction to TLP. So to implement the TLP, the task level parallelism, the processors have multiple program counters because they keep track of multiple task flows. And basically they use a MIMD model based on according to Flynn's taxonomy, multiple instruction, multiple data model, and it targets the tightly coupled shared memory multiprocessors. So multi-core processors that are very popular for desktop and laptop processors, they are basically targeting the TLP, and multi-core processors are one good example of the processor that targets the TLP. So for N processors, basically we have an N number of threads. Now for TLP, we have basically two types of processor implementations. The first type is SMP, the symmetric multiprocessors. This is what you have in your laptop desktop. So multi-core is basically SMP machine. There are small number of cores, and they share a single memory with uniform memory latency. So as you can see from the diagram, so last level cache is shared among processors or cores, and main memory the same. So they have a uniform memory access architecture called UMA, Uniform Memory Access Architecture. The second type of TLP processor is DSM, so Distributed Shared Memory System processors. So the physical memory is distributed among processors, and the processors are connected via the direct and non-direct interconnection networks. And because of the architecture, it takes longer time to access other cores or other processors' memory. So we have a non-uniform memory access. So it's called the NUMA architecture, NUMA, non-uniform memory access architecture. So the term, the shared memory, associated with both SMP and DSM refers to the fact that the virtual address space is shared. So in both architectures, communication among threads occurs through a shared memory space, for example, using pointer operation. In contrast, the clusters and warehouse-scale computers use message passing protocols to communicate among processors because it's very difficult to implement the one single virtual address space. And the MPI, the message passing interface, is one of the most widely used message passing protocol programming paradigm. Now let's talk about multi-core processors. So as we discussed, the multi-core processors are SMP type processors. The threads on different cores share a virtual memory space, and physical memory, the last level cache, and main memory and disk is also shared. So it's a UMA architecture, Uniform Memory Access Architecture, and it targets TLP, the task level parallelism. You can execute the multiple tasks or multiple threads simultaneously. And threads are created by programmers or system softwares. And according to Flynn's taxonomy, it's a MIMD type machine. Multiple instruction, multiple data. So multiple instruction streams have their own data stream on each core. Now let's talk about the last type of data parallelism, which is the DLP, the data level parallelism. So DLP, the data level parallelism, comes from the simultaneous operations across large sets of data. So it's all about data. So basically the idea is we apply the same operation on large sets of data. And there are three popular DLP architectures. One is vector processors, the other is SIMD extension, and lately we have a GPU, the graphics processing unit. Let's begin with the vector architectures. So the vector registers play a key role in vector architectures, and the basic idea is straightforward. So we read a set of data elements scattered in memory into large sequential vector registers first, and then we apply operation on those registers, and we disperse the results back to the memory. And it supports dozens of register-to-register operations on independent data elements, and the registers are controlled by compiler. Next type is SIMD extension. So this is what you have in your CPU. So the SIMD architectures can exploit a significant data level parallelism for data-oriented computing, for example, multimedia applications. And it's more energy efficient than MIMD, multi-core, for example, and it only needs to fetch one instruction per multiple data operation. So it makes SIMD attractive for personal mobile devices because it's energy efficient. The SIMD allows the programmer to continue to think sequentially. And the limitations include there are a number of data operands encoded into opcode, and it doesn't support sophisticated addressing mode like a strided or scatter-gather addressing mode that are supported by the vector processors, and there's no mask registers. So it's like a SIMD extension is like a baby version of vector architecture. Well, the popular implementations, earlier we had MMX, and so MMX evolved into SSE, and lately we have AVX. So Intel and AMD x86 processors have these SIMD extension engines alongside with the main processor. But operands must be consecutive and aligned memory locations. Now let's talk about the last type of the DLP processors, which is GPU. Again, the GPU's main task is graphics rendering, but since 13 years ago, we use GPU as a general purpose processors accelerator, and it's available on almost all modern GPUs. And GPU vendors, we have AMD, NVIDIA, Intel. For mobile GPU, we have Imagination, Qualcomm, ARM, MediaTek, Samsung, NVIDIA, AMD. So the GPU computing is basically running general purpose computation on GPUs, non-graphics application on GPUs. So we use GPU as an accelerator. And the basic idea is basically a heterogeneous execution model. So CPU is a host and GPU is a device, and we run different things on CPU and GPU at the same time. So GPU, the compute intensive and data intensive, the part of the applications are offloaded to GPU and accelerated there. So we have a C-like programming language. So it makes the GPU programming easy, and the programming model is slightly different from SIMD. So it's called a single instruction multiple thread, SIMT. And we have two dominant programming languages. One is CUDA and the other is OpenCL. CUDA is NVIDIA's proprietary. So GPU computing tries to exploit all three levels of parallelism. So ILP on single core, and TLP on multi-core CPU, and DLP on many core GPUs. So it's called the heterogeneous computing. So on GPUs, massive number of threads are running simultaneously. For example, we have a max 8 threads on a quad-core CPU with the hyperthreading, but we have about 100,000 threads on the latest GPUs, and this technology is leading by the NVIDIA and AMD. And we have actually more program languages for GPU. DirectX, which is a part of Direct Compute, which is part of DirectX, and Microsoft C++ AMP, and we have OpenACC. So using those programming paradigms, we can program GPU for general purpose computing. And the GPU plays a key role in heterogeneous computing and high performance computing. So the most top 500 supercomputers are powered by GPUs. So benefits, there are clear and unique benefits of GPU computing. So first is accessibility. So almost every computer has a GPU. So you don't need to buy anything. You just program and your program will run faster. And also it has a interoperability with the display API. And the GPU is small relatively compared to other parallel processors. And it supports excellent the scalability both in both hardware and software. So those are unique benefits, and the GPU is getting more and more popular, and it's changing the landscape of high performance computing.